All right, so no doubt the op-amp integrator is one of the more complicated, if not the most complicated circuits we're going to see. It's not that complicated, but it does combine pretty much all the concepts we've learned in this class. It combines resistors, capacitors, KCL, op-amps, kind of just a grab bag of everything that we've learned in this class, all come together in this one particular type of circuit. So if we want to use an op-amp to integrate an input signal, we would connect as such. Actually, let me draw my op-amp like this, minus plus, and then I'm actually going to connect, instead of a feedback resistor, I'm going to connect a feedback capacitor, which is really interesting looking. And then I'm going to go ahead and ground my input like I've been doing. I'm going to call this V in. This will be my V out, and I'll just call this R, and I'll call this C. This is the op-amp integrator configuration. And so how do we sort of reason about this circuit? How do we know that this circuit is going to take the integral of our input? Well, let's go ahead and do kind of a similar analysis to what we've been doing this whole time. Let's call this current IR, and then we can call the current, we know no current flows into this node, so the rest of the current's going to flow through this capacitor, basically all of it. We'll call this current IC, and we're going to set those equal to each other because we know that all the current that flows into this node has to flow this way through the capacitor, okay? Well, let me go ahead and write out an expression for IR. It's just going to be V in over R, right? If I assume that this, both of these voltages here are 0 volts, then my current through my resistor should be pretty easy to see that it's just V in over R. And how about IC? Well, I know that the current through a capacitor is equal to C times dVc dt. And in this case, Vc, let me go ahead and actually move this here. Vc is the voltage across the capacitor going this way, which in this case is 0 minus V out, or just negative V out. Okay, so let me go ahead and use this expression that we derived, that IR is equal to IC, and I can set these equal to each other. I can say V in over R is equal to C dVc dt, which is going to be equal to C times D minus V out dt. And if I go ahead and divide both sides by C, I get that V in over RC is equal to minus ddt times V out. I can go ahead and multiply both sides by a -1, and I can move the dt over to the other side too, and I just get negative V in over RC dt is equal to d V out. Okay, we're getting close. I've done this derivation a few times actually, where I did a separate and integrate, and this is kind of the same scenario. We've separated the variables. We've got time on one side and voltage on the other side, and we can go ahead, or output voltage on the other side, I should say. What we can do is we can go ahead and integrate both sides now. My goodness, I'm assuming you can hear the ambulance. I can hear it. Hopefully this video doesn't get ruined, but it's just getting worse. So if I go ahead and integrate both sides here, I would integrate here and I'd integrate here. This one's going to be with respect to t, so it's going to be from time 0 to time t. This one's going to be from V out at time 0 to V out at time t. Oh my gosh. Please, I don't want to have to redo this. And so if I were to carry this out, let me just move this up here. I'm going to get -1 over RC times the integral from 0 to t of V in with respect to time is going to be equal to V out at time t minus whatever my initial condition would be. In this case, let's just say that V out of 0 was 0. So basically this V out is starting at 0. So that goes away, and I get an expression for V out of t, which is equal to -1 over RC times the integral from 0 to t of my input signal with respect to time. Okay, so that is where my op-amp integrator integrates the input signal. its output voltage is proportional to the integral of the input voltage, and it's actually scaled by -1/RC. So if I were to put in a DC value here, we know that the integral of a constant is just going to be t times the constant, right? So if I were to write V out of t, if I were actually to plot V out of t, let's say my input was 5 volts. Let's just say that this is 5 volts. Then if I were to plot V out as a function of time, as time goes on, I'm going to have a linear decline in output voltage where the slope of this is going to be -5/RC, right? That would be because I would be integrating 0 to t of 5 dt, which would just give me 5t, and then I'd have -RC coming in from the constant, and so the slope of this line will be -5/RC, right? And that's what we see here. Okay, so that does it for my op-amp integrator example, or that's not my example, sorry, that's just me explaining it, the configuration, and showing you why it's called the op-amp integrator, because it integrates the input signal. The output gives us the integral of the input scaled by -1/RC. And in the next video, I'm going to solve a quick example using the op-amp integrator, and then after that we're going to talk one more time about practical limitations of the op-amp, something we haven't talked about quite yet. I mean, we talked about it briefly at the beginning, but I want to talk about one more big practical limitation of every op-amp circuit, and that'll be the very last slide, and then we'll move on to the very last section of this module, which is very exciting. Okay, so I'm going to go ahead and end this video right here.